Hey guys, this is Mr. Sal. This is a lesson on dilations and proportionality. Thanks for watching. So based on student feedback, this was everyone's favorite unit about transformations. And for that unit, we went over 3 different types of transformations. Translations, reflections, and rotations. Now in that unit, we learned that all 3 of these types of transformations maintain congruency, which means it does not change the size of the shape that we're transforming. All it does is change its location and maybe its orientation. So a translation, for example, would be like taking, well, let's make it a square. We could take a rectangle like this one, and I can move it over here or up here, and that would be a translation. I could also reflect it, which means that there would be some kind of line of reflection, and then it would reflect across that line. Hopefully it'd be about the same size though, which is why it would be congruent. And then a rotation would be taking that shape, and from this point I could rotate it. So maybe from this point I could change the point of rotation and start rotating it here as well. And that would be rotation, but again, it's not changing the size, which is why it's still congruent on that stuff. And that brings us to the 4th type of transformation, which is part of the objective right there, and that is a dilation. So a dilation is going to change the size of the shape, so it is no longer congruent, but we would call it similar. So similar shapes, what you guys should have learned in 7th grade, they maintain that the corresponding side lengths are proportional and all angles remain the same. So you guys have worked with dilations already before. If I were to take this square right here, and I can take that square, and what I can do is I can, what the heck, and I can make it bigger, which is a dilation. So this would be a dilation of that original square from right here. Or if I wanted to, I could make it smaller, which also would be a dilation. Okay? So there's its original, but again, we can make it smaller, which is a dilation, or if we wanted to, we could make it bigger. Again, that's all types of dilations. But again, its size still remains, and its side length still remain proportional to each other for the corresponding sides. When an object such as a line is moved in space, it is called a transformation, which we know already. A special type of transformation is called a dilation. A dilation transforms an object in space from the center of dilation, usually the origin, by a scale factor called r. The dilation moves every point on the object so that the point is r times away from the center of dilation as it was originally. This means that the object is enlarged or reduced in size. For example, if you dilate the set of points 0, 0, 0, 4, 3, 0, and 3, 4 with a scale factor of 2, and the center of dilation is at the origin 0, 0, the distance of each point from the center will be 2 times as long as it was originally. Algebraically, this means that you multiply each point by 2. And we've seen this kind of coordinate rule when dealing with transformations before, but before it was some kind of addition or subtraction. Now that we're multiplying these values, it's going to change the size. To confirm this, investigate this transformation below. 1a, graph and connect the ordered pairs 0, 0, 0, 4, 3, 0, and 3, 4. Take a minute to do that with your neighbor. Alright, so let's put these points on here. We got 1 at 0, 0, 0, 4, 3, 4. I did that at 4, 0, 0, 4, 3, 0, and also 3, 4. So that gives us these points. I'm going to go ahead and label these also. And 3, 4. And also, let's go ahead and connect these points to show the rectangle. There we go. So part B, find the length of each segment and dilate it by a scale factor of 2. Now, scale factor has that word factor in it. When we say factor, what operation are we talking about? That is multiplication, all right? So it's a multiplication of 2. Draw and label the new lengths from the center of dilation, the origin, in a different color on the coordinate plane above. Alright, let's go through this and write in the lengths of each of these sides. So that bottom side of that rectangle would be 3 right there. And then the right side would be 4 units. The top is the same as the bottom, and all the opposite sides are the same length. So we found the length of each of these, and again you can just count those lines or the blocks. But then it says to dilate it by a scale factor of 2. So I am going to use a different color. So starting from the origin, I'm going to make this, instead of a length of 3, I'm going to scale it by 2, which is going to make it 6 units long, which would take us to this point, right here. Well, then I have this length of 4, but I'm going to scale that one up by 2. So instead of 4, now it's going to be 8. So this new length right here is 8. And the bottom length there is 6. And then we're just making a rectangle out of that with the same lengths. This one's still 6. So it's been dilated by a scale factor of 2. And the left side also by a scale factor of 2 has now a side length of 8. Compare the size of the preimage with the image. Okay. Take a minute with your neighbor and compare those sizes of the preimage with the image. Alright, here's what we should realize about the size of the preimage with the image. And just as a, I guess, kind of a quick review, is the preimage is the red shape, which is the image we started with, or the shape that we started with. And the image is after it's been transformed, which is, in this case, the purple one. So comparing the size, all the lengths have been doubled, but what do you guys notice about the area of the red one in comparison to the purple one? What I mean by that is how many of the red ones would fit into the purple one?
2, 4.
4 of them would. So, in this case, the lengths have been doubled, but the area has been quadrupled. Part E, graph and connect your new ordered pairs for the image on the coordinate plane in part A. We did that already. We already have these drawn. So part F, what do you observe about the transformation when you do it graphically and algebraically? Alright, so you can have something written like this. Both times you end up with the same new image. So either way that you do it, algebraically or graphically, you'll end up with the same thing. Let's look at that algebraically though. Alright, algebraically, and we already saw the rule for this one. So the rule, or algebraically, it shows that it's doubling the x's and y's on this thing. So if we looked at the points, including 0, 0, for example, we can start with 3, 0 on the red shape. Then from the transformation, we're going to double those values. So that'd be 2 times 3, and then 2 times 0. And that would give us the new coordinate, or ordered pair, of 6, 0, which is this point right here. 6, 0. So they correspond with each other, and we can continue this pattern. We can also do it for 3, 4. So if the x is 3 and the y is 4, then we replace them into the rule in order to get the new coordinates at 6, 8, which would be this point here in the top right at 6, 8. And it works for these other points as well, like this one, we're going to double the 0 and the 4, so 0, 8. And the origin, if we double that, we still end up with the origin at 0, 0. So these would be the new ordered pairs for the transformed shape. Alright, 1G, how do the lines that correspond to one another in the image and pre-image compare? I'll take 1 minute and discuss that with your neighbor. All right, so we need to see from these lines that they have the same slope and their lengths are also proportional. So if I take the corresponding lengths from the preimage to the image, it will always give me the same ratio, which makes them proportional. So the slopes of these are all the same. If they're vertical, they stay vertical, or if they're horizontal, they stay horizontal. But we'll see other examples on this where they are not horizontal or vertical, or all of them are. We've seen this before, but a special notation is used to differentiate between the preimage and the image. If the preimage is called A, then the image is called A prime, pronounced, again, A prime. 2, try another shape to see what kind of relationship exists between the preimage and the image. Like this one. Take 1 minute and graph and connect the ordered pairs 0, 0, 3, 0, and 3, 4. Alright, let's get these points on here. So I have 0, 0 right here at the origin. Then I have 3, 0. So that's an x value of 3, a y value of 0. And then we have 3, 4. So an x value of 3 and a y value of 4 right here. Then it also says to connect these points. And this will create a triangle for us. Alright, so I'm going to zoom in on this because we're going to need to. But to B, find the length of each segment and dilate it by a scale factor of 1/2. Don't forget the length of the hypotenuse is 5. Oh, that's good. They told us that. We can use the Pythagorean theorem for that. But it also says to draw the new lengths from the center of dilation, the origin, in a different color. Alright guys, since we know the scale factor is 1/2, we know that the new shape is going to be half the size, for the lengths at least. So it should be smaller, a smaller shape. So we're going to dilate this route about the origin, which is 0, 0. Okay? So that point is going to stay the same. On this length right here, we know it's 3. It told us the hypotenuse is 5, and we can count that one as 4. So it's a 3, 4, 5 right triangle. So we're going to double these lengths. I'm sorry, half them. So half of 3 would be 1.5 right here. So that would be that length. Half of the 4 is 2, which goes up this far. And then half of the 5 would be 2.5.
That's so small.
Yeah, it's a lot smaller on this one. And that's okay. Sometimes that'll happen where we have some decimal values. And since the lines don't really account for that, we have by just putting it right in the middle. Label the preimage A and the image A prime. Compare the size of the preimage with the image. Alright, you guys take a minute and do that with your neighbor. Alright. Which of the colors would be A, the preimage?
Red. Purple.
Yeah, the purple one's the one we started with. So the purple one would be the preimage, and the red one would be the image of A prime, of A, which is A prime. So compare the size of the preimage with the image. Each side measures half the length of the preimage. The image is 1/4 of the area of the preimage. And we can see that the red one would fit in that purple one, if we were to kind of draw the lines for it like this. So that's 4 of those red triangles inside of the purple one. So it's 1/4 of the area. Alright, 2D, dilate by a scale factor of 1/2 algebraically using these ordered pairs. So take a couple minutes and use the ordered pairs to show how you would find the new ordered pairs for the red triangle, the A prime. So this is our rule right here. We're going to take the x and y values and multiply them by 1/2, which is what a scale factor will do. So we've got those 3 points for the triangle from the preimage A. I'm going to start with 3, 0. And I'm going to transform this by a scale factor of 1/2. Alright, so this rule, we're taking 1/2 and multiplying it by 3 to get this new ordered pair, which was 1.5 and 0, which is this point on the graph, 1.5, 0. Continuing, if we use the 0.34, so we already have the 1/2 multiplied by the 3, but 1/2 multiplied by the 4 is 2. And that, again, is this point right here, which is 1.5, 2. Finally, we can take the origin, which is at 0, 0. If we multiply these by 1/2, then anything multiplied by 0 is 0. So it still gives us the origin at 0, 0. So this is how you would show algebraically, using the rule, how to find the points or the corners of this, the ordered pairs for this image. So there we go, we've already found those ordered pairs. Alright, graph the new ordered pairs for the image. We did that already also. So part F, take a minute to do this with your neighbor. What do you observe about the transformation when you do it graphically and algebraically? Talk about that. So on 2F, what do we observe? Again, you should see that either way that we do it, whether it's algebraically or on the graph, we end up with the same new image, that red image, A prime, either way. So 2G, how do the lines that correspond to one another in the image and preimage compare? Take 1 minute and write a sentence for this one with your neighbor. Again, we're showing that on that red line, on the red shape rather, the image, A prime, all the sides that correspond to one another have the same slopes, whether it's undefined or 0 even. And also the lengths are proportional. So again, the lengths on this shape, on the A there, this is a length of 2. This one was 1.5. And then this one was half of the 5 at 2.5. So again, we're just cutting each of these parts in half, which would make them each proportional as we compare them to corresponding side lengths, which we will do more explicitly in the next problem. Now that you know how a dilation works, you will investigate what kind of relationship is formed between the preimage and the image after the dilation, which we kind of already have. So take a minute with your neighbor and do 3A through D. Just follow the instructions, and then you will complete 4 through 7, which is on the same page. So take a couple minutes to do that with your neighbor. We'll go through that, and then we'll look at each question individually, numbers 4 through 7. So just to start off, 3A, connect points B to C. Okay, that's not too bad. There we go, we did it. 3B, double the length of AB on line AE, and we'll label the new segment AB prime. So we're just doubling that length, which right now is 4. So the new one will be 8 units, and it'll be away from A. So this would be considered the point B prime from A. 3C, double the length of AC on the line AD. Label the new segment AC prime. Okay. Since that C is above B, we should kind of know that it should be above B prime as well. So our new point would be right here at C prime. And then we will connect that A and C prime as well. Now we don't need to worry about the length of that right now, but what we do want to know is the length of CB is 2, because then it tells us connect B prime to C prime, which would be this length. And since we know it was doubled the length, that 2 has now transformed into a length of 4 since we doubled that length. What do you notice about the segment B prime C prime in relationship to BC? Take a minute and write one sentence about that with your neighbor. Alright, we kind of did discuss this already, and we saw that BC is 2, and B prime C prime, that segment is 4. So all we've done is doubled the length of BC to get the length of B prime C prime. So what do you notice about the size of the two triangles? Take a minute and write a sentence for that one with your neighbor. Alright, we've seen this before, but the image has an area that is 4 times the area of the preimage. Which means if we looked at that triangle, and let's say we made it blue like this, we could fit 4 of those blue ones into the red one. Number 6, write a ratio that compares the corresponding parts of the preimage with the image. Alright, for this one we're going to need each of the lengths. So let's look at, we'll make that blue triangle. We've got 4 and 2, and the red one has lengths of 8 and 4. And we're not worried about the hypotenuse on these ones, particularly because this triangle, both triangles, give us the slope of that line AD, which is something we need to remember on this one. So if we were to compare this, for example, CB, and let's say we wanted to compare that to the segment C prime B prime. Well, the length of CB is 2, and the length of C prime B prime is 4, and this would simplify into 1/2. On the other hand, if we compared AB line segment to its corresponding side of AB prime line segment, then let's see what we get on that. So AB is 4, AB prime is 8, and when we simplify this one, we also get 1/2. Now again, this is kind of a ratio showing that each of these are proportional, so the fractions are equal. And part of that, and we've discussed this before, but that's because this line is straight, which means it has a constant rate of change, so the slope is going to be the same no matter what. What this also means is that we can find slope no matter how big a triangle, right triangle, that we draw from a line segment like AD. This will be crucial as we move forward in this unit. Alright, number 7, what kind of relationship exists between the preimage and the image? Take 1 minute and write a sentence for that one with your neighbor. Alright, so this is what I got. The corresponding parts of the image and preimage are proportional to one another, which we've seen already. If we looked at how we would do the slope on this, right? For example, the red one, that shows an up 4, and then to the right 8. On the blue one, it's up 2, to the right 4. Again, we're showing that these are equal even if we compare the same parts of the triangle. And it gives us a slope that would be 1/2 for this line right here. Alright, thanks for watching again, you guys. If it helped you out, please subscribe to the channel and make a comment below. And give the video a thumbs up. We'll see you guys later.